Hello, y'all. Welcome to lesson 140 of my DP chemistry curriculum. Today we're doing structure 3.2.10 and 11. These are HL topics. In 3.2.10, we're going to look at proton nuclear magnetic resonance spectroscopy, or HNMR, the one referring to the mass of the hydrogen proton, which gives information on the different chemical environments of hydrogen atoms in a molecule. So we'll interpret HNMR spectra to deduce the structures of organic molecules from the number of signals, the chemical shifts, and the relative areas under the signals, represented by integration traces. Then in 11, we're going to look at individual signals, which can be split into clusters of peaks. We will look at HNMR, specifically high resolution HNMR, to show splitting patterns showing singlets, doublets, triplets, and quartets to deduce greater structural detail. And we're going to look at data from the data booklet. This will be in section 21 of the data booklet, I believe. So with that said, let's just talk about what proton NMR is, or proton nuclear magnetic resonance. And this will be the only time I write the whole name out. HNMR. Now, I'm going to ignore writing the one on the hydrogen just because I'm lazy, but technically it should be there, but I will not write it for the rest of this, so don't comment or whatever. So basically, this is one of our analytical techniques. And it's used to determine the number of different chemical environments of protons, specifically hydrogens, of protons in an organic compound. So what the heck does that even mean? And how does this work? Because we need to know a little bit about that to kind of figure any of this out. So first we have to think about protons as quantum particles. They are charged particles with a positive charge, and as such, protons spin around their axis. Which, if you have any idea of physics and like the right-hand rule, a spinning charge generates a magnetic field. And because they generate a magnetic field, they can also align with a applied magnetic field. Now, when they align with a specific magnetic field, we'll actually get two spin states. So we will create two spin states, because they'll be spinning one way or the other way, which will create opposite magnetic fields, which means they'll be either parallel with the magnetic field or anti-parallel. And that is based on direction of spin. So in HNMR, we're going to apply a magnetic field, which will align these protons either with or against the magnetic field. Now, when they are aligned with or against the magnetic field, they actually have different energy levels or energy states. Specifically, anti-parallel have slightly higher energy. Oops. Slightly higher energy. And that difference in energy, the delta E between states, is equivalent to approximately a radio wave. Which is very interesting because the energy of the radio wave can then promote that lower proton to the higher energy state, the parallel with the anti-parallel. So the energy of the wave equal to delta E will have a resonance frequency, meaning it's at the frequency that it can promote that difference. And so basically what happens is with that resonance frequency, and this kind of sounds almost like the promotion of electrons between energy levels, but really we're promoting protons from a lower to higher energy state. But with that resonance frequency, we can cause lower energy protons to promote to higher energy state. So we now can apply radio waves into this magnetically aligned field of protons to promote our lower energy protons to that higher energy state. So that allows now very specifically those protons to fall back down. So this is the key aspect now. When promoted protons fall, they release the same energy or same frequency, seeing as these are related, which is detected detected by our detectors, but it's detected, which creates a spectrum that we can then analyze. So all this is to say, for HNMR to work, we take a sample containing a lot of protons in an organic compound. We blast them with the radio waves to we align them with a magnetic field, then blast them with radio waves to promote the parallel to the anti-parallel energy levels. We let them fall back down, and then we capture the released radio waves, creating a spectrum, which looks like this. So this is the spectrum we get. We're going to talk about this in just a bit more detail later, but specifically, we're going to get this spectrum right down here, which has peaks that show different chemical environments. And I'm going to describe this whole thing in just a moment. But HNMR shows, chemical environments. So what are chemical environments now? Those are just groups of protons with the same resonance frequency. So from our image, we see we have some protons with this resonance frequency, some protons with this resonance frequency, and protons will have different resonance frequencies based on their chemical environment. But what that basically means is that they all have the same bond, same chemical bond. So how do we define those chemical bonds or those chemical environments? The best thing to do is to look at an example. So in this example, let's look at ethanol. So ethanol has carbon with 3 hydrogens bonded to a carbon, double bond oxygen, single bond hydrogen. If we look at each of these 3 hydrogens, they actually represent the same exact bond. Hydrogen is connected to a carbon, which is connected to a carbon, double bond oxygen, single bond hydrogen. Again, same thing. And if we think about this in 3-dimensional space, they're all equidistant away from everything else. So all 3 of these carbons might be in chemical environment A, or hydrogens might be in chemical environment A. So all of these protons will produce the same resonance frequency. Meanwhile, This hydrogen is connected to a carbon which is double bonded to an oxygen. That strong electronegative force from the oxygen creates a much more upshifted bond between that hydrogen. I'll talk about that word in just a moment. But basically, we can now see that all of A, these are what we would call equivalent protons. They all represent the same resonant frequency. However, if we look at A and B, these would be considered non-equivalent. I guess I put the quotes after protons. So this would represent two different chemical environments. Which would represent two peaks on HNMR. So our HNMR diagram of ethanol should show us two peaks. Let's take a look at another example. And we can start getting some hints about how this works. So in this case, I'm just going to do ethane. So maybe pause and take a moment. See if you can figure out how many chemical environments we have. Which protons are equivalent protons, which protons are non-equivalent protons. So pause it and come back. All right. So this is actually a case where we can use a plane of symmetry to see that all of these are equivalent protons. So we would just see one peak, all equivalent protons. Each hydrogen has exactly the same bond as the others. Let's try one that's just a little bit harder. And in that case, we're looking at one peak. Let's look at butanoic acid. So with butanoic acid, we have a 4-carbon chain. It's a carboxylic acid, so it ends in COOH. And here it is. So pause, take a moment, and try and see how many different peaks or different chemical environments you have, and I will come back in 3, 2, 1. So in this case, definitely we have that one by the as part of the alcohol to have its own peak. Now, if we look at each individual carbon and hydrogen, these hydrogens are the same. They're on the same carbon and they feel the same force from both sides. So this will be its own. This will be its own. And this will be its own. So hydrogens on the same carbon will always feel the same force. However, the adjacent carbons will cause their adjacent hydrogens or bonded hydrogens to feel these different forces. So we actually have 4 chemical environments. So we'd expect 4 peaks in our spectra. So now going back to spectra, how do we actually interpret it? Well, there's a couple aspects we need to focus on. There's specifically 4 different aspects. First, the number of chemical environments is shown by signals. We saw that in that example above. Furthermore, the protons, or the type of protons, in each environment is shown by chemical shift. This is specifically our x-axis. So when you look at your x-axis, that's our chemical shift, and it is measured by section 21 of data booklet. So when you look at your data booklet, this is what you see in section 21. I'll bring that onto the page in just a moment. After that, the ratio of protons is shown by the integration trace. So the integration trace is that fancy blue line above. Now, that basically just shows the area under each peak. So integration trace comes from the word integral. Integral is the area under the curve. So the integration trace shows us the area under each peak, which specifies the ratio of protons for each signal. We can usually count. They're always going to be in whole numbers because it's just a simple ratio. Now, the last part, which we'll not do quite yet, but we'll come to it at the end of this lesson, is that the number of adjacent, hydrogens is shown by splitting patterns. Specifically, these only show up high resolution HNMR. So we're going to do some examples. Well, we're going to do one example where we show low resolution HNMR. And then we'll talk about high resolution HNMR at the back half of this lesson. So the last thing, it's not specifically a point, but basically all measurements. So everything we see are relative to tetramethyl silane, also known as TMS. TMS has a chemical shift of 0. So we get all our data from this standard called TMS, and we're actually also going to talk about TMS in a little bit after we do an example. So let's go back to our example. So we have a couple things here that we can now give some kind of words to it. First off, we have our chemical shift. Which is measured in parts per million. And we now know that chemical shift of 0, because it says so right here, is TMS. So this is a relative peak. We don't actually measure from it. This is just kind of what we use to standardize our entire data. So we're actually going to ignore this. So we ignore that peak. Now, we do need to look at our values for our chemical shift, but we need our data booklet so that we can reference it. So I'm going to go ahead and add in section 21 from the data booklet. And we'll lock it here so we can zoom in. So we have a couple values. I kind of like to start from the left and go out to the right. So we have this value at 9, maybe 10. Now, this is that high value, which shows us an aldehyde group. So we can likely tell that this 910 value is an aldehyde. One of the things that helps us see that is our integration trace is a ratio. I'll use a color that shows up a little more. This is about a 1 to 3 ratio, which means we have about 1 hydrogen here for every 3 hydrogens here. So this is going to be our aldehyde, which makes sense with our 1 to 3 ratio because an aldehyde only has 1 hydrogen. So that's an aldehyde at about 9.5, maybe 9 or 10. All right, so then what is this big peak here? This peak is kind of at about 2.2, and it has 3 hydrogens. It's a little odd though, because this is definitely too high up. It's at 2.5 to 3.5. This is 2.2 to 2.7. So it seems like it might be here with our ester, but there's an issue. There's only two hydrogens and we know it's a 1 to 3, meaning there's only one possible option, and it's going to be CH3. So how do we explain that? This must be CH3. So at 2 ppm. So how do we justify this? Because this chart is a little off. First off, if it's CH3 in an aldehyde, this must be ethanal, just because ethanal is a 2-carbon chain with an aldehyde and CH3. But why do we have CH3 so much higher than 0.9 and 1? That's a question that we have to figure out. It's actually kind of this weird phenomenon. CH3 should be at 1. However, proximity to oxygen, because in ethanol it's right next to a carbon double bond to oxygen, causes what we call de-shielding. What that basically means is that the peak moves down field. So that's a term I used earlier, basically meaning more towards 10 or to the left. And basically, because these signals come from the resonance between the bonds of hydrogens, a very strong electronegative atom like oxygen can cause that resonance frequency to cause de-shielding, which shifts our signal downfield. So this is still CH3. This still makes sense with our integration trace as well. So that's HNMR, specifically low-res HNMR. I definitely suggest trying some practice problems. You can go onto Cognity, or you can just go online and ask Google to generate, or not Google, any of the AIs to generate some HNMR problems, or just look for some low-res HNMR problems. So let's take a moment to talk about why TMS is used. What is it? Why is it used? Well, first off, TMS is just silicon with 4 methyl groups. So first off, TMS is super unreactive, as you can guess from all the methyl groups, and non-toxic, meaning it's safe to use in a lab. It's also very volatile. Remembering that volatile doesn't mean explosive necessarily, but just it's easy to become a gas. So this is easy to remove. You can just boil it off at very low temperatures. So you can remove it from your sample to purify your sample once you've done your testing. Furthermore, all protons are equivalent. All protons are equivalent. And you'll notice there's 12 of them. What this does is it produces a strong upfield signal. That we equate to 0. So that's why we use TMS. It's always going to be our strongest upfield signal, and we just base everything off that. Upfield meaning more to the right. So that's TMS. All right. So we've talked about low-res HNMR. We've talked about TMS. So now let's address number 4, splitting patterns. What the heck are splitting patterns? And we'll do a couple practices with these because these are a bit harder. So splitting patterns, we learned it comes from high-res HNMR, which specifically shows splitting. But that doesn't really give you much in a definition. So what the heck is splitting? Splitting is where peaks split into multiplets or multiple peaks. And a multiplet is basically just a splitting pattern based on interaction between adjacent non-equivalent protons. So this basically is a big, very term-heavy way of saying that hydrogens on neighboring carbons will affect each other, causing that peak to, instead of being a nice smooth peak, split into these weird multiple peaks or multiplets. So we have 4 peak types. This is for DP specific. So DP only cares about 4 peak types. The first one is simple. It's called a singlet. It's just one sharp peak. Second one is a doublet, 2 peaks. You can probably guess. Now we're going to have a triplet, 3 peaks. And then we're going to have a quartet, 4 peaks. And these come from what we call the n+1 rule. So we have all our different rules, but the n+1 rule basically states that we just count adjacent non-equivalent protons and add 1. So very simply, let's go ahead and look at a compound. Here we go. So, oh, let me just scooch that around. So this is the peak of ethanol. You'll notice our integration trace is still a 1 to 3 because ethanol has a 1 to 3 when we look at our diagram. We know a couple things about this. This comes from our CH3. This comes from our aldehyde. Now, if we look at our CH3, there are 3 hydrogens with 1 adjacent non-equivalent hydrogen, meaning that we will have a doublet because n+1, 1 plus 1. Meanwhile, if we look at our aldehyde side, our COH, that has 3 adjacent hydrogens, 1, 2, 3. So 3 plus 1 is 4, and we have a quartet. So high-res NMR allows us to see these different aspects of our signals. Not only do we get the base information, but now we can see the adjacent non-equivalent protons that exist. So that's kind of what we use high-res HNMR for. Let's do one more example. This one's going to be a little bit harder. So in this example, there's no integration trace, but this is going to be ethanol. So we did ethanol, this is now ethanol. Now, ethanol's a little bit funky. So if we look at it, it has I'm going to change colors here. CH3, CH2, OH. So we should have three discrete peaks. A, B, B, C, C, C. So we have these three discrete peaks. Of course, we have TMS, and we had TMS up here too. So we can ignore the TMS peak. We have to now look at these and kind of figure out, well, what's going on here? Well, the weird part with ethanol, and specifically anything that's that has a hydroxy group that we have to take into account, is that the OH does not affect splitting patterns. So because of that, if we look at CH3, this is our CH3, we have a triplet. That comes from the two Bs. If we look at all the way over here, this is going to be our CH2. We have a quartet because it's only affected by the CH3 carbons because, again, OH does not affect this. And then lastly, we have our OH. OH right here is just going to have a singlet because it is not part of this. It does not affect splitting patterns, so it itself is not going to be affected by splitting patterns either. So with that, this makes it kind of one of those very weird examples, but you should start trying to expose yourself to as many examples of HNMR so you can start figuring it out. So anyways, I hope this helps and have a great day.